We've talked about CUs, control units, in previous lessons. We'll just go ahead and focus a bit on them for this lesson. Let's explore how the control unit of a CPU interprets instructions and coordinates the execution of those instructions. This is a critical part of how programs run and how attackers might exploit low-level CPU behavior to manipulate execution, making it obviously relevant for your cybersecurity studies. The control unit, CU, is a component of the CPU responsible for fetching instructions from memory, decoding them to figure out what needs to be done, and directing the rest of the CPU to carry out the instructions via these control signals. The CU acts like a traffic cop. It does not execute instructions itself, but it tells the ALU, arithmetic logic unit, memory, and I/O devices how to execute them. The control unit drives the CPU's core cycle, the fetch, decode, and execute cycle. For fetch, the CU retrieves an instruction from memory using the program counter, and the instruction is stored in the instruction register, the IR. For decode, the CU decodes the binary instructions into a set of signals that can activate the appropriate CPU components. It identifies the opcode and the operands. For execute, it's via ALU, the arithmetic logic unit, or memory. The CU triggers the ALU or memory unit to perform the required operations, add, move, jump, and so on. It may update the PC, as in the case of a jump or branch. Now, once the control unit has decoded the instruction, it moves to the execute phase. Depending on the type of instruction, the execution step is handled by different parts of the CPU, primarily either the arithmetic logic unit or the memory unit. The ALU is responsible for all arithmetic and logical operations like addition, subtraction, logical and or XOR, comparisons, bit shifting, or rotating. In these cases, the data being operated on is already inside CPU registers or fetched from memory beforehand, and the ALU performs the computation. The result is often stored back in a register. Some instructions involve moving data to or from memory, RAM, not performing calculations. These are load, store, or move instructions, and these interact with the memory subsystem. Move stores the register value to memory. Load and store instructions in other architectures do the same in more explicit terms. Push and pop are those stack operations also working with the memory. In these cases, the memory unit, in conjunction with the memory controller, carries out the instruction, not the ALU. The CU activates memory access logic and addresses, often involving the data bus. The distinction matters for the purposes of improving efficiency. CPU resources are specialized, and ALU handles that math and logic. Memory handles the data movement. So we're using only what's needed to conserve the CPU cycles. For security and side channels, understanding which component is used is important because memory access timing can leak data, cache-based side channel attacks, for example, while ALU misuse might relate to logic bombs or overflow exploits. And instruction scheduling. Modern CPUs might schedule ALU and memory operations in parallel on different execution units, so distinguishing them allows for pipelining and out-of-order execution. Certain instructions, especially control flow instructions like jump, call, return, and J and Z, result in the program counter being directly updated. These instructions might not use the ALU or access memory in the traditional sense. Instead, the CU modifies the PC to redirect the instruction flow. Operation scheduling refers to how the CU decides when to execute instructions and in what order, especially when things like instructions depend on each other with data dependencies, or multiple instructions are issued per clock cycle in superscalar or pipelined CPUs, and resources like memory or ALU are shared or limited. So those key scheduling concepts, pipelining is for overlapping stages of different instructions to improve throughput. Out-of-order execution is for reordering instructions to make better use of CPU resources. And hazard detection, the CU identifies data or control hazards and may stall or reorder execution to avoid errors. Understanding CU behavior is important in cybersecurity for reasons such as there are timing attacks, where attackers measure how long certain operations take to infer secrets like cryptographic keys. And side channel attacks, the CU-driven scheduling decisions might leak data through power usage, heat, or timing variations. And those speculative execution vulnerabilities. CPUs often guess which instructions to run next to stay fast, and the attacks like Spectre and Meltdown exploit this speculative behavior to read that protected memory. So think of the control unit CU like a factory supervisor. Each worker ALU memory register file has a task, but they wait for the instructions from the supervisor. And the CU decides what task comes next, who does what, when to pause or proceed. If data isn't ready, the supervisor reschedules or stalls the line. And this is how a CPU handles dependencies or hazards. The control unit is vital in orchestrating instruction processing within the CPU. In cybersecurity, knowing how instructions are scheduled and interpreted helps you understand where low-level exploits might occur, such as timing attacks, speculative execution flaws, and register manipulation. So the control unit is a hardware component built directly into the CPU's silicon. It's not software or firmware, though it interprets and acts on software machine code instructions. The CU is implemented as part of the CPU's internal digital logic circuits, designed to carry out specific control tasks like instruction decoding, signal generation for coordinating CPU subcomponents, and managing timing and sequencing of operations. It's physically etched onto the microprocessor die using transistors, just like other CPU elements, ALU, registers, cache, etc. Now, a transistor is that fundamental building block of modern electronic devices, especially in CPUs and memory. At its core, a transistor is a tiny electronic switch that can turn on or off to control the flow of electrical current. It allows computers to process binary data, ones and zeros, which is, of course, the basis of all digital computing. A transistor has three main parts: source, drain, and gate. So the source is where the current comes from, the drain is where the current goes, and the gate controls whether the current flows. The gate receives a small voltage. Depending on whether this voltage is present or not, the transistor allows the current to pass, that's on or 1, or it blocks the current, which means off or 0. This binary switching is how transistors are used to represent bits in logic gates and memory cells. To list a couple of examples. Now, logic gates, the AND, OR, NOT, NOR, etc., are built using combinations of transistors. The control unit, ALU, registers, and cache all use transistors to perform computations, store state, and route signals. A modern CPU has billions of transistors, so the more transistors, the more complex and capable the processor. The most common type in modern CPUs is the MOSFET, that stands for metal oxide semiconductor field effect transistor. That's tiny, it's a nanometer scale, fast, and power efficient. At the electrical and physical level, the control unit is made of logic gates, those fundamental building blocks that combine to perform logical operations. The finite state machines, FSMs, to track and control which stage of execution is currently active, fetch, decode, execute, etc. The multiplexers and decoders for selecting between instruction paths, components, or signals, and the timing clock control circuitry, ensuring operations happen in the correct order and duration. There are two major types of CU design. The hardwired control unit uses fixed logic circuits to generate control signals. It's fast and efficient, but it's inflexible. You have the microprogrammed control unit using a small ROM to store micro instructions, defining how each instruction is handled, easier to modify or extend. The modern processors might blend these approaches for speed and flexibility. So while not everyone in cybersecurity deals directly with the CU, the control unit, there are specific roles and specializations where a deep understanding of the control unit is very helpful. Reverse engineers analyze binary code, how it's executed on hardware, and understanding the CU helps them map out control flow and hidden logic. The firmware and hardware security analysts investigate attacks at the CPU or microcontroller level, including instruction hijacking or privilege escalation. The exploit developers leverage timing, speculative execution, or instruction-level bugs, all tied closely to CU control unit behavior. And the red teamers, and offensive security experts. They create low-level payloads with shellcode and understand how instructions are dispatched and executed. And then academic researchers explore side-channel attacks like Spectre and Meltdown, which involve CU-controlled execution timing and branch prediction. So even for roles not directly interacting with the CU, understanding its function enhances comprehension of how instructions are executed, how vulnerabilities are exploited, and how low-level mitigations work, like pipeline flushing or speculative execution barriers.